Great. Yeah, thanks a lot. Thanks for the introduction, and yeah, thanks to the organizers for having me here today. Yeah, so I'm excited to tell you about the Kikuchi hierarchy and Tensor PCA. I'll tell you what all these words mean in a second. And this is joint work with Ahmed and Chris. Okay, so to sort of set the stage for the type of problems I want to talk about, I'd like to talk about problems coming from high-dimensional statistics. So here's one very classical problem of a high-dimensional statistical problem to sort of give you an idea of the type of problems I think about. So this is called the planted clique problem. The idea is that there is a random graph, so a G n1/2, that means n vertices. Each of the potential edges occurs independently with probability 1/2. But then there's also going to be a planted K clique, right? So I mean, that means K vertices chosen at random, and all of those vertices connected to each other. So that's what's shown in red here. And the goal, this is sort of a statistical inference task, is that I give you this random graph with the hidden clique, and your goal is to find the clique, right? And it's sort of an algorithmic task. So we're interested in using a computer to solve this on a very, very large graph. And what's maybe striking about this problem is that it is believed to have what's called a statistical computational gap. So this means that as K, so K, remember, is the size of the clique. So, and you think of K as sort of a signal to noise ratio. It's, how large the clique is. So as K increases, the problem goes through 3 different phases. At first, if the clique is too small, it's simply statistically impossible to find the clique. Right? We're interested in finding the clique with high probability. And so when the clique is too small, when it's smaller than sort of the cliques that would naturally occur in a graph of this size, you simply won't be able to find it, no matter what algorithm you use. Now, if the clique size is quite a bit larger than that, square root n instead of log n, then we call the problem easy. Easy for us means that there is a polynomial time algorithm. So in this case, you can use a spectral method. So take the adjacency matrix and look at its eigenvalues and eigenvectors, and this will help you find the clique, for example. But sort of the most sort of interesting and elusive regime here is the middle, where we call it hard. So hard means that statistically, it's possible to solve the problem if you're willing to check every possible clique, but we don't know an efficient or polynomial time algorithm to do this. Right, and we sort of conjectured that this is fundamental, but really there does not exist a polynomial time algorithm. And so the key question I want to sort of talk about is, how to understand this. What makes statistical problems easy versus hard? And this is somewhat different from classical complexity theory, right? We know that the max clique problem is NP hard, but this doesn't mean it should be hard to solve an average case or a random instance like this. And so the types of evidence we have for why this random problem should be hard is a bit more subtle, and I'll get into some of those types of evidence.
Alex, could I just interrupt you to say that there is a question from Dima, if that's all right? So go ahead.
Thanks. Sorry to interrupt. I was just curious, these regimes, do they correspond to this random matrix situation with outliers where if you take a large random matrix and add a finite rank perturbation, then for small values of the perturbation and kind of gets absorbed and then you can't see it. And then for large ones, there's a spectral consequence of it.
Yeah, that's exactly right. Like in these spiked Wigner or Wishart matrix, right, you have like the BBP transition or right. So exactly, yeah, this K equals root n is sort of the point at which you start to see this one eigenvalue sort of jump out from the rest, and this one is correlated with the eigenvector is correlated with the position of the clique. Yeah, that's exactly right.
Thanks.
Okay, so this is sort of motivation. This isn't the actual problem I want to talk about today, but what I want to talk about is some general methods for attacking these types of problems. And one method actually is inspired by statistical physics. Okay, so what on earth does statistical physics have to do with these types of computational questions? right? So there's all these different high-dimensional inference problems like planted clique, but also the other ones listed here. These are all, roughly speaking, problems where you have some kind of a planted signal corrupted by some kind of noise, and you want to find the signal. And the connection to statistical physics is the following, that when you do inference, you might be interested in the posterior distribution. That is, given the data we observe, what is the posterior distribution of the planted structure? And it turns out that for these types of problems, this posterior distribution follows what's called a Gibbs or Boltzmann distribution. And this is the same type of distribution that's used in statistical physics to model disordered systems like magnets and so on. And so a lot of the equations that govern these things are the same as the equations that govern statistical physics systems. And coming from statistical physics, there are a few different algorithms that are popular. So the first is called belief propagation. I won't tell you exactly what it is, but roughly speaking, you should think of it as having a bunch of different agents that are all talking to each other. So in this case, in the case of the clique, you could think each node, each vertex in the graph, is talking to other vertices saying, I think maybe I'm in the clique, and that means maybe you're in the clique, or, I'm not in the clique, so that means you shouldn't be in the clique, or these types of ideas, these types of messages. And, after repeating this for a long time, they sort of converge to something which is hopefully the right answer. There's also something a bit more sophisticated called approximate message passing. You can think of it as sort of a simplification of belief propagation that's easier to analyze rigorously in certain settings. And these two approaches together have been hugely successful, often giving extremely sharp and precise results about phase transitions between easy and impossible problems. And oftentimes this is simply the statistically optimal thing you can do. But in other times, these things are not statistically optimal, but still it's sort of often believed or conjectured that these are the best types of algorithms among all efficient or among all computationally polynomial time algorithms. And so if belief propagation or AMP fails, this is sometimes taken as evidence that there should be no polynomial time algorithm for this regime of parameters. And so this theory really has been hugely successful at precisely understanding both, what should be the statistical limits of the problem and what should be the computational limits, right? Understanding where these three phases, impossible, easy, hard, occur. So that's sort of the statistical physics view of these things. There's also a sort of maybe competing view or alternative view, which is based on something else called the sum of squares hierarchy. So I'll briefly talk a little bit about this, although you won't need to know the details of how this works because it's maybe a bit complicated. But what is the sum of squares hierarchy? It's sort of a systematic way to get convex relaxations of polynomial optimization problems. So just about any problem can be written as a polynomial optimization problem, something like planted clique or what have you. But these are not tractable to solve on their own, and so we want some kind of convex relaxation that we can solve efficiently. And you can take higher and higher degrees of these relaxations, which sort of get stronger in that they better approximate the problem you want to solve, but they also take more and more runtime as you go up this hierarchy. And so this sum of squares method also has been hugely successful at giving the best known algorithms for all kinds of different problems. And it too has a way of giving us evidence for when problems should be computationally hard. This is called sum of squares lower bounds. And this is, if you prove that sum of squares cannot solve a problem, then this is sort of constitutes evidence that maybe no algorithm can do it, no efficient algorithm. And so sort of the meta question that I'm interested in today is whether we can unify these two approaches. We have on one hand statistical physics, on the other hand sum of squares. Do these kind of make the same predictions about when things should be hard, or if not, which one is right? And so specifically for this talk, I want to talk about a specific problem called Tensor PCA. And this is actually a problem where statistical physics and sum of squares disagree, sort of surprisingly. But we'll sort of talk about how to fix it and make it so that they actually do agree. Okay, so this is the Tensor PCA problem, which is the actual problem I want to focus on for the rest of the talk. Also called the spiked tensor model. So there's a couple different ways to think of this. There are n variables that are plus minus 1 valued. And you think of this as the planted signal that you want to recover. This is called x. Maybe a easy way to think of this problem is the first bullet point down the bottom, where it says for every p variables, you get a noisy observation of their parity. Right, so p is just some number, some fixed number, the tensor order. Right, so for every subset of every collection of p of the underlying plus minus 1 variables, we get a noisy observation of their parity. By which I mean we observe this thing. This is called YU. It's lambda, so lambda is just a number, the signal to noise ratio. We observe lambda times, the actual parity of that subset. That is the sum of the x values on that subset, and then plus Gaussian noise. Right, that's one way to think of the problem. Maybe, since I know all of you are familiar with tensors, an easier way to think about this in tensor notation is what's written at the bottom, where what we're really observing is a rank 1 tensor, the x to the tensor power p, plus a Gaussian, IID Gaussian tensor, symmetric tensor. Okay, so you can think of this as a rank 1 tensor corrupted by additive Gaussian noise. Okay, is the model itself clear? And if you're familiar with the spiked Wigner matrix model, this is the case p equals 2, where you just have a matrix. Okay, so how we have this problem called Tensor PCA. This was motivated by various practical applications, and so people wanted to understand, what's the best way to solve this. So, how should we try to solve this problem? Maybe the first thing to try is what's called maximum likelihood estimation. So we think about what is, given the data Y we observe, what is the posterior distribution of our planted signal X? And we can sort of write down what this is explicitly. And then we want to look for the X that maximizes this, right? What is the most likely signal given our observations? And what this boils down to, it turns out, is to just maximize this inner product between the observed tensor and the tensor power of our guess, right? So find the guess V that has the best agreement with this truth, or with the observation rather. Okay, and this has been shown to succeed provided the signal to noise ratio is above a certain threshold. And this turns out to be essentially the optimal thing you can do, statistically speaking. Okay, but why is this not the end of the story? Well, because this requires exponential time, right? In order to actually do this, you need to check every possible candidate V in order to do this argmax. So this is, statistically speaking, basically the best algorithm. Computationally speaking, we would like something better. Okay, so if we want to be computationally efficient, or we want a polynomial time algorithm, what can we do? Well, there's a large class of what's called local algorithms, which roughly speaking means you're going to keep track of some guess V for what you think maybe the true vector X is. And we're just going to sort of make local updates to this somehow, or in a way that maximizes the log likelihood. Right, we want to sort of make local improvements that make this vector a little bit better and see if this gets us to the right place. So this includes things like gradient descent, something called tensor power iteration. Longevin dynamics is sort of a continuous time version of gradient descent in some sense. And also this champion algorithm from statistical physics, approximate message passing, which has been very successful in other settings. Also is sort of a fancy version of a local algorithm like this. And these succeed up to some other threshold, which is not as good as the maximum likelihood, but some other power of n. Okay, and then maybe a third type of algorithm we can look at is the sum of squares hierarchy. So people have looked at the sum of squares program itself, which is a semi-definite programming problem. Also, people have looked at sort of simpler spectral methods. That is, build some matrix and look at its eigenvalues and eigenvectors that are sort of inspired by sum of squares. And another spectral method called tensor unfolding, which is actually quite simple. This basically just means you take the tensor you're given and you kind of find a way to flatten it into a matrix by combining some of the modes. And you then just take the leading eigenvector of this. Okay, and these things work up to some third threshold. And sum of squares lower bounds actually suggest that this is sort of the right threshold for polynomial time, that maybe no polynomial time algorithms should be able to do better than this. Okay, and so I know I've talked about a lot of different thresholds, so let's draw a picture of what's going on here. So this is a plot of what happens as lambda increases, right? The signal to noise ratio, how strong is the signal, right? So if lambda is too small, it's simply statistically impossible to solve the problem no matter what you do. Then at some point the maximum likelihood starts working, but right, this is not an efficient method. So then we have sort of this hard regime where we don't know any polynomial time algorithms. Then at some point, sum of squares starts to work, or these other spectral methods. But what I want to highlight here is that there's a gap between sum of squares and these local algorithms, right? These sort of gradient descent or other methods like this work strictly worse than sort of the best known polynomial time algorithms. And this is maybe sort of a surprise or a, kind of a shocking gap, that things like gradient descent are really not the best thing you can do here. And this includes, AMP, which is this, algorithm from physics, which really has been hugely successful at all these different problems, also fails here, fails to get the right threshold. Okay. So, and this is sort of not, not the end of the story. If we look a little bit more closely, there's something more subtle going on, which involves what's called subexponential time algorithms. So if we don't just care about, polynomial time versus not polynomial time, we can be a bit more specific about what actually runtime are we looking at. So we can look at these sort of intermediate runtimes that are 2 to the n to some delta. Right, so faster than fully exponential, but still slower than polynomial. And Tensor PCA turns out to have sort of this nice smooth trade-off between runtime and statistical power. So as the signal to noise ratio increases, the runtime of the best known sub-exponential time algorithm sort of smoothly decreases. So don't worry about the specific formula here, but basically this sort of interpolates smoothly between the two algorithms we know already. So if I set delta equals 0, this is saying that I have a polynomial time algorithm at sort of the sum of squares threshold I mentioned before, whereas delta equals 1 means that there's a fully exponential time algorithm for at the sort of MLE threshold. Okay, so this is all happening within the hard regime. It's saying that inside the hard regime, the problem gets harder in sort of a smooth way, that it smoothly goes from exponential time down to polynomial time as you increase the lambda. And this is sort of in contrast to a lot of problems, especially some problems where statistical physics has been used to predict sort of sharp phase transitions in the past. A lot of these other problems actually have like a very sharp transition. You say maybe when lambda goes past 1, you suddenly jump from being polynomial time to being fully exponential time, which is quite different from what we see here. Okay, and so one observation is that for these soft thresholds, like the one in Tensor PCA, belief propagation, or AMP, right, these algorithms from statistical physics, somehow cannot be optimal, or at least they can't be the end of the story, because in these situations, BP and AMP are basically linear, essentially linear time algorithms. And for something like Tensor PCA, you expect to be able to do a little bit better by moving to, say, a quadratic time algorithm or cubic time, right? By making your runtime a bit slower, you should hope to be able to get a bit more statistical power. And this is something that belief propagation and AMP cannot do, at least in their vanilla version. As sort of an aside, there is a kind of a concrete reason we have actually for why this particular subexponential runtime is the best one, we believe. This is something called the low degree likelihood ratio. I won't spend too much time on it, but basically there's a relatively simple calculation that seems to predict how much computational power is needed for these kinds of questions. This was originally inspired by sum of squares. And the idea is to sort of look for a polynomial that solves the problem. So look for a polynomial of the input, a multivariate polynomial of y, that can, say, distinguish between the planted spike tensor we're given versus just pure noise. So what this equation here is saying, maximize over polynomials. In the sense, we want to find the best polynomial who has a large expectation, right? It outputs a big value if it's a planted distribution, and this divided by its sort of fluctuations in the null model. So the polynomial is supposed to output a big value under P, small value under Q. And if there is such a polynomial, that achieves a large value, say tending to infinity as the problem size gets large, then this sort of means that we expect there is a degree D polynomial that works. And then sort of the underlying conjecture here is that degree D polynomials actually seem to be as powerful as algorithms of time n to the d, at least for these types of problems, these types of high dimensional statistics problems. And so this gives some kind of concrete evidence for why this exact trade-off is the best one. And so there's a survey here on this you could look at for more, but I won't spend too much more time on this now. Okay, so let me tell you finally what our contributions are. Right, so I've told you that sort of Tensor PCA is a problem where these BP or AMP type methods seem to fail, which is sort of a failure of this whole statistical physics type of approach. And we sort of remedy this by giving a hierarchy of increasingly powerful BP type algorithms. So similar, the same way you have the sum of squares hierarchy, increasing algorithms of increasing power, but also increasing runtime. We have the same type of hierarchy of these message passing algorithms. Specifically, it's based on something called the Kikuchi Hessian spectral method, which generalizes what's called the beta Hessian. This is a previous method to build a spectral method. I won't get into too much what this means, but it's based on something called the Kikuchi free energy, which is proposed a number of years ago. And what we prove is that these new algorithms match the performance of sum of squares. So both it gets the right polynomial time threshold and also the same exact subexponential time trade-off. Right, so this sort of refines the statistical physics approach, saying there's not just this belief propagation algorithm, but really this whole hierarchy of increasingly powerful things you can do. And somehow this redeems the statistical physics approach in some sense, because now now the statistical physics and the sum of squares methods actually agree on what should be the right answer, or what should be the optimal algorithms. And one benefit of this is that the algorithm analysis is actually a lot simpler than the previous sum of squares methods. In this talk, in the last few minutes, I'll try to give you an idea of the algorithm for just even order tensors, although we have a few other extensions too. So let me try to tell you what exactly is this algorithm. I'll later explain, why you should think of this as sort of a message passing type of algorithm, or why it's sort of like a higher order belief propagation. But for now, let me just try to define this matrix that the algorithm is based on. So remember, we get this tensor, right? It's sort of indexed by subsets of size p, and we pick some integer L, right? L is sort of the level of the hierarchy that we're going to try to use. And we build this matrix based on symmetric differences. So the matrix is indexed by subsets of size L. Okay, and what do you put at each entry of the matrix? Well, you take your two sets, S and T, both subsets of size L. You look at their symmetric difference. Symmetric difference is what's shown in the picture, right? The elements that they disagree on. And if that has size exactly P, well, then that means we have an observation about this set as symmetric difference T. And so we plug in that observation, Y sub that set. And otherwise we just put a 0. Right, so this is sort of this complicated matrix with some kind of combinatorial structure. Okay, I'll give you a second to look at this, ask questions if it's not clear. Okay, and so what do we actually do with this matrix? Then we just compute the leading eigenvalue and eigenvector. And then there's a simple way to round this to an actual solution, right? You get an eigenvector of size like n to the L, but there's a simple way to extract from the solution that I'll talk about in a second. Okay, and the runtime of this is basically n to the L because that's the size of the matrix itself. And so one basic case, if you take the smallest allowable L here, this recovers a previously known algorithm called tensor unfolding, which basically just means you take your tensor and flatten it to a matrix and take the eigenvectors of that. But you can also keep moving up the hierarchy and getting these bigger and bigger spectral methods. And these match the same performance as the sum of squares hierarchy. And this algorithm, it looks maybe unusual, like where did this all come from? But this was really derived in a principled way. There's sort of a systematic way to derive this using this principle called the Kikuchi Hessian, but I won't get into exactly how this works. But I do instead want to try to convince you why you should think of this method as sort of a higher order message passing algorithm, right? I want to give some intuition of what this algorithm is actually doing.
Alex, just to say 5 minutes left.
Thanks, yeah. Okay, so what is this algorithm doing? So remember, this is just a definition of the matrix. So you take, it's indexed by these subsets of size L. Each entry is going to be 0 if the symmetric difference does not have size P, and otherwise it's the corresponding value of Y. And so I said we were going to compute the top eigenvector of this. One way we could imagine doing this is just by running power iteration, right? Start with some guess vector and keep multiplying this by our matrix. And so this guess vector is a vector of length n choose L, right? And I want to think of this as being an estimate of each entry of this V sub S. I want to think of it as being sort of an estimate of the parity of the set S. Right, just the product of, right, remember the x's are just plus minus ones that we want to recover. So x is the true signal. And we're working in this space where, instead of just keeping track of a guess for x, we're keeping track of this big vector that's keeping track of these higher order guesses, right? What does it think the parity of each set is of size L? Okay, and then if I just sort of write down what is power iteration, right? What does it mean to multiply a vector by m? Just by expanding the definition of m, here's the formula I get. And I want to sort of interpret this. So remember that y sub some set is a noisy measurement about the parity of that set. And also the v sub a set is you think of it as a noisy measurement of, or a noisy guess about the parity of that set that comes from the previous iteration. right? This left arrow just means that we're updating, the new v sub s is equal to this formula. And what I want to say is that this v sub s is going to be the sum of many terms coming from different sets t of something, right? This y sub, right, s symmetric difference t times v sub t. And the idea is sort of that I want to think of it as these different sets kind of talking to each other. So all the sets t that interact with s in the right way, with the right symmetric difference, are sort of sending s a message about what they think s's parity is. Right, so that's what this term is. And then s is sort of summing up all of these incoming messages and sort of averaging all that information to get sort of a guess. Right, so what's happening, you should think of each of these terms being summed up as being like t's opinion about the parity of s. Because if you exactly knew the parity of t and the parity of s symmetric difference t, you could multiply those together to get the parity of s. And so instead we have sort of two noisy guesses for those things, and we multiply those together. Does this make sense? So the idea here is this can be thought of as sort of a higher order message passing algorithm among sets of size L, all sort of talking to each other. Okay, and that's sort of the key idea of the algorithm. The way to analyze this is actually quite simple. If we think about an even simpler problem where we just want to distinguish between the planted tensor and pure noise, like is there a planted signal at all? Remember, we build this same matrix, and the key step turns out to be bounding the spectral norm of this matrix when you just plug in random noise for the y's. And the point I want to make here is that the analysis is actually extremely simple and just uses sort of this matrix turn-off bound sort of out of the box. So since our matrix luckily is just what's called like a Gaussian sum or series, you just have sort of the sum of IID matrices with Gaussian coefficients in front of them. You can basically just use some very standard matrix concentration to analyze this algorithm very easily, which is a lot simpler than some prior work. Okay, I know I'm a bit short on time, so let me wrap up. Some related work. There's also been a sort of morally similar kind of message passing algorithm proposed before, although we couldn't quite get this one to work in our setting. Some independent work based on, inspired by quantum, actually came up with sort of a similar algorithm as well. And there's sort of also a different way to sort of redeem these local algorithms by running multiple copies of gradient descent in parallel. Okay, so to summarize, we saw that local algorithms are surprisingly suboptimal for Tensor PCA. These are some local algorithms. Right, they keep track of an n-dimensional state and try to update this. And we somehow, redeemed these local algorithms and redeemed the AMP by giving this hierarchy of higher order message passing algorithms that keep track of these higher order correlations and now match the best known algorithms based on sum of squares. And the proof was simpler than prior work. A couple of future directions are whether we can unify these two approaches more generally, not just for this one problem, Tensor PCA, but can we say something sort of for all problems in some sense? And also whether one can systematically obtain optimal spectral methods more generally. So we use this Kikuchi Hessian approach here. Unfortunately, it doesn't seem to work for all problems. And so this is still sort of an open question. All right, thanks very much for your attention.